Hello everyone, welcome back to MLC. Thanks everybody for waiting. So after 1 week of break, we are coming back to our machine learning compilation lectures. This is lecture 6. And we're going to talk about how can we, integrate everything we learned so far and trying to ask the question about how can we tap from existing machine learning frameworks such as, PyTorch, JAX, and other frameworks onto a machine learning compilation process, which we will then be able to use the techniques like automatic program optimizations and a few other deployment techniques that we're going to talk about in the follow-up lecture. Okay, so again, this is more like an interactive course, so we're going to do a more like interactive session today with IPython notebook. The notebook will be available on the course website, and you're more than welcome to go and check it out. In the meantime, we're also going to have companion exercises, possibly a few days after the lecture. So hopefully, you will also try things out by yourself by running them through those companion exercises. So to begin with, we are going to still install necessary dependencies. In this lecture, we're going to actually use PyTorch as an example. So we're going to import PyTorch. And specifically, we're going to use Torch's module called FX, which we are going to use to capture some of the input computation graph from PyTorch. But before we do that, let's review a few of the high-level concepts. Some of them we have actually used some of them in our assignments exercises, but hopefully we want to actually go deeper onto some of the background so that at least for a lecture, you will be more prepared for understanding what's really going on. So anyways, we are going to talk about this API called Tensor Expression, or TE, which is a domain-specific language that we use to help us create a set of tools for us to be able to create a tensor. Okay, so to begin with, we are going to talk about So to begin with, we're going to talk about an API called Tensor Expression that help us to create a set of TensorIR functions. Okay, so I'm going to walk you through some of the Tensor Expression API. We have touched upon it in some of our past lectures, but we're going to review it so that we can get a better understanding of what's going on here. First of all, we're going to import TE from TVM namespace, and we're going to create two placeholders. In this case, these two placeholders effectively creates two temporary nodes in a computation graph. What we're going to do next, we're going to try to connect them with the matmul function that we're going to introduce next. Okay, so each of the TE placeholder in here is of type te.tensor, and in here, the TE tensor simply represents a possible state or nodes in the computational graph that we can use to compose up the TensorIR functions. Each of the TE tensor have its own shape field and d-type field. So in this case, we already specify the shape is 128. So you can find that a.shape is equals 128. In order to compose up a set of computations, one of the things that we can do is through an API called t.compute with the following signatures. We're going to specify the output shape and how we're going to compute each element of the output matrices. And we're going to do that through this particular function. So you can find that in this particular function, what we do is we take two TE tensors A and B. And what we're going to do is we're going to compute a result of n and m. So in this case, A's shape is n by big K, and B's shape is K by M. And we're going to compute the result whose shape is n by M. The way we are going to compute matrix multiplication is through this formula. So what it says is that for each of ij element, we're going to compute AIQ times BIK and sum it along the reduction axis whose shape is A.shape. One of the things you might notice is that when we write this particular TE matmul function, actually we do not directly say that n and m equals 128. Right? So this is a generic function that's actually going to work for any A and B with different kind of shapes. And this is kind of a common pattern in Tensor Expression library that help us to build up generic tools to compose up those programs and generate TensorIR functions. So once we define T matmul, we'll be able to call C equals T matmul, and that gives us another computational graph. So after this computation, effectively what we're going to have is we're going to have A and B in here that points to C as a computational graph node, and the operation here corresponds to effectively this matmul operation, or this particular compute operation that we have here. So TVM create tools allows us to take this computational graph and try to convert it into a prime function or TensorIR function that we're interested in. So because each of the loops, each of the compute here describe a set of loops, effectively we're going to convert some of them onto loops and computation. So let's see what happens. One thing we can do is we can call t.create prime function by passing all the parameters of interest. In this case, we are passing in both the input and output parameters. And there's a new API called show that allows us to directly display the highlighted code of in the TVM script form. So let's try. So you can find after we call create prime function, it gives the prime function. If you show it, you'll find that it corresponds to a TensorIR function here that corresponds to A, B, and in this case, the matmul is of my output C buffer. And there will be a list of input. There will be a list of loops that generates a matrix multiplication operation that we're interested in. So one of the things you can find is that actually tensor expression is a way for us to concisely describe some of the tensor expression operations. There will be cases in that we might still need to write TensorIR functions, and in the future, actually, we are going to interplay some of the TensorIR functions in TVM script together with the tensor expression API as well. You can view like tensor expression API as it's a way for us to stitch together some of these expression computations, and we can convert them onto a TensorIR function of interest. So right now we have done the matrix multiplication function. Let's create another function called ReLU. In this case, we can leverage some of our Python features to actually create a generic ReLU function. So we can find that in here it is a lambda function. The star I means that we can take any set of positional arguments. So effectively what it says is that I can do lambda I result of A of I, and it's also another function that lambda I1, I2, two arguments, A of I1 and I2, and so on. So effectively, this particular t.compute actually works for A of arbitrary dimension, actually, in this case. We can also try it out. For example, I can allocate A of one dimension with shape 10 by time, and we can pass it through t.ReLU. You can create prime function, and you'll find that you will get the result that computes this ReLU of input 10. Right? We can also pass in another x with 10 by 20, and you can find that the same function works. So you can find that this is kind of like interesting pattern. Here we are using a tensor expression function that help us to effectively generically create different kind of programs that fits into different input shapes and output shapes. Another thing that TAPI allows us to do is allows us to compose up and create some of the fused operators in a single TensorIR function. For example, what we can do in here, so we can create a matrix multiplication and apply a ReLU, and in this case, we're only going to create a final TensorIR function with the input and final output. So we are not going to so the only input output we're interested in, we're going to input A and B, and we're going to output D because C is an intermediate result. We're not going to include in the parameter list. In this case, the create prime function is going to automatically create the intermediate temporal value. So you can find that it's A and B, and this ReLU, there is going to be a matmul, which is temporal variables that correspond to C that allocates inside the function. And here's a matmul logic followed by ReLU logic. So this is a way for us to create TensorIR function that are kind of like having a matrix multiplication and ReLU fused together. Normally, we don't have to do it in the model ingestion stage. However, this is a very useful tool in certain cases where that you know that fusion is going to be helpful. It's also a useful tool for us to generate fused operators in some of the future transformations. In the last example, we did not pass intermediate result C into argument list, and in some cases, it can be helpful to also pass in C, which means that we are going to say that, hey, I'm going to create a function where the memory of C is also not being allocated inside the TensorIR function, but I'm going to allocate outside. And we can do that, and you will find that this final function is going to contain additional argument called matmul that corresponds to C, and this is a program that runs it. In most of cases, we want to avoid passing intermediate values so that the allocation happens inside. There are more optimization opportunities, but in certain cases, there are use cases where you can directly pass in C as well. Okay, so far we talked about how we can create a single TensorIR function through Tensor Expression API. So moving next, in order to build end-to-end executions, we still need to be able to connect multiple TensorIR functions together through a computational graph. Let's talk about the block builder, which is a tool that helps us to incrementally build a relax function. So as a first step, what we're going to do is we're going to declare what we call relax variables. So in a computational graph, every node A and B correspond to a relax variable in here that is just a variable placeholder that points to that particular computational graph node. So first, we're going to create two relax variables with the corresponding shape. And in here, we're also indicating the general type. So in this case, we are indicating the number of dimensions here and the data type of the particular relax variable here. In order to build an end-to-end computational graph function, we are going to use what we call block builder. And here's the code block that constructs an IRModule. So you can find that it contains several steps. There are a few scopes that we can define that creates a certain function scope within that particular computational graph function. Recall that particular data flow construction refers to that every computation inside that block is going to be not have side effect. So they correspond to computational graph functions. And then we have several operations in here that correspond to computational graph operation that we're going to walk through later. And if we run this, you will find that we're going to get an IRModule in here. And if we show, here's a module. So let's try to scroll it a bit. You can find that it looks quite similar to what we have done manually in the past lectures, right? Especially if you look at this particular function, this corresponds to the computational graph part of it. And then you have TE matmul and TE ReLU that correspond to the particular TensorIR function that runs through. If we take a quick look at this particular computational graph function, you can find that you have input arguments in here. And the first thing we do is we're going to do call here that calls into this particular tensor expression functions using what we call destination passing convention that we talk about in the end-to-end execution section. And then we're going to do call ReLU that calls into this particular function. Finally, we're going to return. So in this case, we are marking this GV as a global output variable that's accessible outside the data flow block. And then the return value of the function is GV in here. So this looks quite similar to what we write manually, right? And if you compare the particular set of block builder code that's needed to generate this particular module, you can find it certainly shorter in a sense. So that's one of the reasons why we want to use a builder to be able to incrementally build up things. Okay. So let's take a deeper dive into block builder APIs. In this case, it's helpful to look at both the block builder code as well as the corresponding relax function side by side. So here's the corresponding relax function. I'm omitting all the TensorIR functions. If you're interested, you can scroll up to see the original TensorIR functions. And then there's the relax function. There's the block builder set of procedures on the left-hand side. And we can find that there's almost a direct correspondence between the left-hand side and right-hand side, right? So you have function here, function, data flow block scope, which directly correspond to here, and this emit TE metmul correspond to this line correspond to this line, and so on. So you can find that it's almost a direct correspondence between the builder part as well as the generated TVM script code. And if you look at the elements in here, you can find that first of all there are scopes in a block builder that indicates that hey, here's a set of scopes I'm interested in. I'm in right now, and as a result, the follow-up actions like those emit actions is going to generate an instruction or actually in this case it's a binding within that data flow block. Another thing to note is that all intermediate variables in the IRModule construction, like C in here, is generated by this function called emit_te. And this function, what it does is that it will try to create this call to tier to the tier function. Actually, TE metmul in here is different from this TE metmul. The TE metmul here is a tensor expression function that we defined earlier. And then the TE metmul on the right hand side is the TensorIR function that sits within this IRModule. What's happening here is that when we call emit_te, under the hood, the block builder is going to create a TE placeholder and tensors, run that TE metmul compute, then use create prime function that we just mentioned earlier to create that particular tensor function, put it into the IRModule, and then create a call tier into that. So it does quite a lot of steps in here. And in the end, it's going to return a corresponding data flow variables in here, and C is a particular pointer or reference to that data flow variable. So you can find that C types data flow var. The data flow var is a special instance of relax variable. So as we mentioned before, in this computational graph looks like A, B, and goes to C that correspond to TE metmul, and then goes to D that correspond to result of TE relu, right? And each of these intermediate results is being pointed as a relax variable, and data flow var is simply a subclass of relax variable. It indicates that it's an intermediate value within the data flow, so it's not going to be referenced by anything outside. So it helps us to kind of bound the scope, right? So we know that C is inside the data flow block, inside the computational graph. For a variable to be referenced outside, it need to be marked as output. So in this case, GV is a variable that can be referenced by outside and returned to the other blocks, or being used as an input to another data flow block if the function contains multiple data flow blocks. So we have already talked about what's happening under the hood in the emit_te call. For example, if you take this particular line is generated by C equals bb.emit_te in here, and under the hood, emit_te does several things. First of all, it will create t.placeholder for A and B, which are relax variables, and then it will run them through the TE metmul function, which is tensor expression function we use to generate the corresponding tensor expression. And then it will call into create prime function to create a corresponding TensorIR function. And finally, it will try to generate a call onto the corresponding TensorIR function through call tier. So the result computation graph contains two intermediate values, including the result of TE metmul and the result of the TE relu operations. We also mentioned that we can create output variables of each of the data blocks through the emit output. That will create an output variable that can be referenced by outside of data block. The reason that we do this is we want to try to distinguish between what are the intermediate or internal computation graph nodes that are not being referenced by outside, and what are the computation graph nodes that are being referenced by outside. So as we start to try to change the content of data flow graphs, we normally would only change the internal node of the data flow. Finally, on the function side, we will be able to mark the return value of the function in here. In the block builder, there are two ways to mark return values. The first way is that the first way is when we mark the return value, we can also specify the parameters to the function. So in this case, A and B are being specified when we emit output. This is actually a very useful way to specify things because in a lot of cases, the number of parameters is unknown as we start to build these functions through translation. So we want to collect them on the fly. So we are just going to do it in the end. On that hand, if the parameters are known beforehand, actually it's also helpful to do it another way, right? So directly specify it in the with function, so it looks a bit more like a function signature that we have. And in practice, we kind of encounter both, so the API support both modes, but you can either do one way or another, otherwise you will cause an error in the block builder side. Okay, so we have learned so far all the basic tools of building a computational graph using a block builder and the Tensor Expression APIs. Moving next, let's start to talk about how can we leverage those tools to really interface with the machine learning frameworks. In particular, in this lecture, we're going to talk about how can we bring in models from PyTorch onto the IRModule, as well as a consequence of following up MLC flow that we're going to use in this lecture and follow-up lectures. So to begin with, let's define a model in PyTorch. So in here, I'm assuming that you are familiar with PyTorch. There are a lot of online materials that teaches about PyTorch about intelligent checkout, but I'm also going to walk you through the code in here. So in this particular case, this is an example that defines matmul value, which is the same as a matmul value that we use as a running example in the first part of the lecture. And this is the torch.enum module that defines a matmul value operation, right? So you can find that first of all, it specifies a parameter as a parameter, it specifies a weight as a parameter. Then it will run through matmul and value in here in this forward function. So once we have this, what we can do is we can create this module, and we're going to use a specific utility inside PyTorch called TorchFX. So TorchFX is a way for us to actually symbolically trace the corresponding PyTorch model as a computational graph module here. And this is a relatively newer feature, but it's a very useful feature for us to inspect what's really going on in a PyTorch model. There are certain limitations, like the computational graph cannot contain control flow. It have to be a pure data flow graph, but it's useful for a lot of machine learning models that we see today. And in other cases where you want to interleave things like control flow and other things with the computational graph, we can also try to use TorchFX to trace part of the model, doing MLC within that part of the model, and trying to put that back onto the PyTorch flow. So in this case, I'm using TorchFX, and we're going to use a symbolic trace API to trace a particular FX module. Within the FX module, it will have a graph representation that effectively shows what is the computational graph view of this model. You can find that in this case, there's two operations, matmul and relu, and here's output, specifies input. So effectively, the computational graph looks like xw, which is a weight. We will have matmul in here, and then the result of matmul goes into relu. So effectively, this is the computational graph we are looking at. So one of our goal is, of course, one thing I can do is I can try to directly use IRbuilder to construct the same function, right? But on the other hand, the main purpose here is we want to try to define something generic, so that we can not only doing manual translations of this particular PyTorch model, but we also want to create a tool so that allows us to be able to translate almost arbitrary or a majority set of FX modules that are being traced in PyTorch. Okay, so the way to do that is we want to do is effectively a translation step that starts from a PyTorch FX module and computational graph, and try to turn that onto an IR module that TVM recognize. Okay, and to do that, the first thing we want to do is we want to try to create a few mappings. So there are a few things we want to map through. The first thing is we want to be able to map the parameters in the original computation graph onto the corresponding constants, in this case of the target IRModule, because we are using constant to embed parameters in here. And this is the first thing we are doing here. So this is called map parameter function. What it does is that it takes in a torch.n parameter, and it's going to create a relaxed constant. In this case, we are going to get a numpy array of that constant, and the type of that constant is if the dynamic type that have n dimension. And for here, let's assume that I'm only going to convert 32-bit floating points. Of course, I can make this more generic so that the data type corresponds to the data type that the parameter corresponds to. So, but for simplicity, we are going to make a simpler implementation here. And another thing so here, this handles the particular parameter part, right? And next thing we're going to do is we're going to iteratively iterate through the computational graph. For each of the computational graph node here, we will try to create a mapping that maps the original computation graph in the TorchFX is in the type of fx.node. We're going to map it onto the computational graph node type that we recognize in a block builder, which is a relaxed variable that represents a translated node in the corresponding function. And finally, we do want to be able to as we iterate through the fx graph, we want to be able to find the output of the node. We want to find the mapped output of the node given the input. Okay, so I'm going to walk you through this translation function. It's going to be slightly long, but I think it still fits into roughly one screen, so hopefully it's still a reasonable implementation. Okay, the main logic is this from fx function in here, and let's take a look at this function. So what it does is that it takes the fx module. That's a module that we have which contains the computation graph representation from PyTorch. Because we're going to create something that's specialized to input shapes, we're going to give input shape list of input shapes in here that help us to know that information. That also helps to deduce intermediate shape. And usually, the input shape only specifies what's the shape of the input to the model, not parameters. So in this case, it's just the input x. And then there are two additional maps, both are dictionaries, that tries to map. It's a dictionary that says, for each of the core torch function and core torch module, how do we handle that? So we are not going to define the corresponding mapping function here, but we're going to define them in a later part. Let's now assume that those maps are available in here. Okay, and then what we're going to do is we're going to walk through the logic. So first thing we're going to do is we're going to create a block builder. And in here, we're also going to create a node map. So the node map tries to map from the original fx node onto the translated node in the target computational graph. And what we're going to do in here is, first of all, we're going to create this function called main. And because fx is a purely data flow block, and corresponding pure data computational graph, we can just encapsulate it as a computational graph block. Okay. The next step we're going to do is I'm going to iterate through the nodes in the fx graph. In this case, the nodes in the fx graph are already in topological order, so it's safe to just iterate through in this topological order. And we're going to handle the translations of each kind of node. The first type of node is placeholder. So this placeholder corresponds to the input of the computational graph. In this case, we are going to just get the shape of a corresponding input. This input index is stateful, so it counts, how many input we encountered so far. And we're going to create a relaxed variable with a corresponding name, shape, and the type that correspond to the number of dimensions and data types in here. And we're going to also collect it as a list of inputs to the particular function. And then we're going to say that, I'm going to map this particular node onto this input variable. So in this case, for this particular graph, this is x, and x type is placeholder. So I'm also going to draw the computational graph here for clarity. So this is mapped x weight here, and the placeholder here is, when you encounter x, it's going to be hitting this line. Okay. The second thing is getAtter. So this part we can safely skip it actually. In this case, getAtter effectively try to fetch a weight within FX module. So this fetch ATTR function, that's the implementation on top. You don't necessarily have to read it. It's a utility that specifically provided by the FX example code. And what it does is simply tries to do FX mode dot weight. In here, it simply get that attribute. Okay, that attribute is a parameter. We're going to call map parameters to map that to a relaxed constant. And I'm going to record the corresponding mapping in here. What's more interesting is when you encounter things like call function and call module. And this particular is in our particular case of this example, actually, we're going to encounter a call function. And in this case, when you encounter call functions, this call function can be torch. The call function node target can be torch dot relu or torch dot matmul. Okay, and in here, what we're going to do is we're going to use a dictionary to define the corresponding translation logic, because there are so many torch functions that that need translations. And the translation logic will take in a block builder, a node map, and the corresponding torch node. So what's within the translation function, what happens is that the corresponding translation function, say TorchRelu, is going to look up the inputs of the node and in the node map, so to get a translated inputs, and then use block builder to build the translated output and return to here. And we're going to put that back onto the original node map. Similarly, there is a call module. In this case, the module corresponds to an earn.module, and we'll be able to actually get the corresponding module here. So the only difference here is that module can contain weights, right, that are implicit. So besides the original, besides the node in here that contains the inputs to the module, we also need to pass in the name of the module in the translation function, and we're going to look at the particular case of translation function later as well. And finally, if it's the output, I'm going to record output in here. This translator is specifically built assuming that there's only one output, and it's not hard to generalize it to multiple outputs actually. And then I'm going to emit my output in here and find as an output of computational graph. And finally, the function output is being recorded in here. One thing to notice is that we are using a pattern of collecting the function parameters during the translation phase, right? So that's why we are putting the parameters in the end in here. Finally, we are getting our IRModule in here. Okay, so far so good. At least it fits into one screen. Right? Hopefully, it's a reasonable translator we can do to bring functions from PyTorch to the IRModule. Now we have these functions. What we can do is we can go and apply the translation APIs. In particular, remember that we will still need to specify the call function map that says that specifies how we're going to map each of the torch function. And then we also need to specify call module map. In this case, our particular example don't contains module calls, so we are only going to specify the call function. And here's how we're going to implement the matmul map, right? So effectively, the logic looks like this. First of all, I'm going to take an FX node.args correspond to the inputs of this particular function, and node.arg0 is the input node of so for example, arg0 likely correspond to x. And in my previous translations already populated a node map to map x to the corresponding relaxed variable. So I'm going to effectively get the corresponding relaxed variable here, and relaxed variable b. And then I'm going to call emit te of te matmul in here to create another computational graph node that runs the matmul operations. Okay, so here's how we translate matmul. Similarly, we can do call emit te into TRelu to translate the corresponding relu function. If I'm going to run this, from TorchFX not defined, I need to run this function first and try this again. And you can find that we get an IRModule that looks almost like what we would manually build, right? So you find that we will have a relax function that corresponds to combination graph that calls into matmul, relu, and the corresponding matmul relu function in here. Okay, so far so good. So to summarize, the general idea of how we interact with the existing machine learning framework is that almost most of machine learning frameworks contain some form of computational graph representations. And what we can do is we can do a translation step that takes in a computational graph, or sometimes a sub-computation that also can represent a computational graph, do a topological order transversions, right, and try to create a mapping from an original computational graph node in the computational graph in the framework, in this case PyTorch, onto a computational graph node in our IRModule, in this case a relax variable. And then we use block builder to incrementally build up this corresponding function. Of course, along the steps, block builder also helps us to build things like TensorIR functions, the particular implementation of primitive functions in here, right? And another thing to notice is that we can easily customize the translation rules. For example, in certain cases, maybe we are interested in not mapping matmul onto a tensor expression function, but I'm interested in mapping that onto, say, direct calls onto libtorch, or calling into a lower level function like COD, and we can easily customize that either in the translation step. In other cases, you can translate first and then do further transformations to transform the IRModule to leverage the other kind of abstraction that implements the same feature. Okay, so far we have learned about how we have learned about simple examples of bringing in computations from PyTorch onto our IRModule and MLC flow. Next, let's coming back to the fashion MNIST example that we used in the past few lectures and see how we can bring a somewhat real-world PyTorch model. It's not real world, it's toy model, but a model that can predict fashion MNIST classes onto IRModule. So in this case, that looks like a sandal. Hopefully, it is a sandal, maybe. And then recall that our model, right? So our model is a 2-layer linear neural network. We have used this model in the past few lectures. We can build it up using a MLP model in here. And then I'm going to populate the weight manually using the NumPy arrays that we had in before. And then I'm going to, one thing that we can do is we can run the code through the MLP models, get the argmax, and it gives you the right prediction. So this is the PyTorch's prediction in here. Now let's try to translate it from PyTorch onto our IRModule and see if we can use the same set of logic if we can reproduce the same set of logic. Okay, and in this particular case, this model actually leverages n.module, so it does contains named modules within this particular set of computation. And so as a result, we will need to be able to define what we call core module map that tells the system how we're going to map each of the modules. In this case, linear and relu in here. Okay, and here's how we're going to define mapping of linear and relu. In particular, the mapping of linear is quite interesting. So besides the FX node, we're also going to have n module. So that's corresponding to the n module we're going to invoke. One of the things that we care about in the n module is the weight, right? So we want to be able to map parameters of a weight to create a constant in here. There's a node map in here. And then in this case, there's a bias. So we also need to map the bias term. One thing I'm using here is, see, I'm calling a topi.n.den. So in this particular case, topi is a set of predefined tensor expression APIs that defines a set of operations. Effectively, it's a predefined thing so that you will be able to directly call into them to construct a set of tensor expressions. And topi.n.dens directly correspond to x matrix multiply of x and w transpose. And then what we do in linear is we are going to do matrix multiply and add function in here. So in this case, we are translating linear as a single functional block, right? That contains both matmul transpose and bias that. In other cases, you don't necessarily have to do that. We will be able to actually translate it into a single. Oh, actually, in this case, actually we are translating into two functions. So there will be a dense function in here and an add function in here. But if you choose to do in another way, we will be able to construct a single tensor expression function that does fused, dense, and add, which is also possible. And if you look at the ReLU function, it's actually simply called into map ReLU because the same mapping logic in here. And if you're going to try this one, you can find that we're going to get slightly longer IR modules that contain several functions. You have add here, dense here, ReLU function, and another add that's specialized to a different shape, and another dense that's specialized to a different shape as well. So this is our main function in here. And you can find that it contains a dense operation, add, ReLU, dense, add, and the constants are the corresponding constant that we created through map parameter. Okay. Once we have this IR module, what we can do is we can try to run it through our compilation flow and then try to run the prediction using our tool, right? Using the MLC flow. And you can find that it gets the same prediction. Okay. Okay, so far we have walked through several ways to interface with machine learning frameworks. And up until now, we are trying to map most of these PyTorch operations onto calls into TensorIR functions, which is relatively lower level and it's quite flexible. It allows you to create different mappings for optimization purposes. In sometimes it's actually helpful to translate those computational graph node not directly into call into TensorIR functions, but also call into built-in primitive operators. And in this particular case, I'm going to customize the original mapping function a bit. So in this case, I'm going to say that instead of trying to map into a tensor expression function for now, I'm going to call relax.op.ReLU and relax.op.add. And those ops are just building ops that relax have. And if you run this, you'll find that it's going to return you a concise relax function that have add, dense, ReLU in here. And this is a typical, actually, this is a more typical computational graph that you will see in a traditional computational graph framework. So in the TVM, we support both the higher level abstractions like these primitive building tensor operators, as well as calls into TensorIR functions. Throughout MLC process, eventually, we will want to convert those high-level primitive operators onto lower-level implementations. So that will mean that we'll need to convert those higher-level operations onto calls onto library functions or onto a TensorIR function that then get code-generated. And normally, if we are doing translation step, usually it's sometimes helpful to convert those operators first onto those building higher level primitives when possible, because they allow us to defer certain decisions. For example, if I have relax add dot here, I can say that I can map that onto say CUD add library or a code-generated code later. So I can defer that decision using when I get a high level primitives. That's an advantage of high level primitives. On the other hand, in a lot of cases, the higher level primitives are not always available. So when we're doing machine learning computations, there always needs to create different kind of computations. And in certain cases, maybe I just want to write things like instance sum operations and other operations. And in a lot of those cases, actually, it's much more convenient to directly specify TensorIR functions. And we also encourage you to do so because a lot of optimizations that follow-ups actually can work with the TensorIR calls directly, and also offers a broader range of coverages. In other cases, there are opportunities to actually directly specify, hey, I just want to try out what's the effect of directly using CUD in this particular case. So you will be able to, instead of translating that into a high-level function, you can directly translate it onto a library call in this case. Usually what we find is we can get the best result by combining a mixture of high-level operator calls, tensor library abstraction during translations, or actually doing those transformations after we ingest them onto IRModule. We'll discuss those trade-offs in the follow-up lectures. But one takeaway here is that there are certainly different ways to do translations and trying to represent the same operations. And one of the things in MLC is we want to enable those different ways in the same abstraction and being able to translate among them, being able to build them and translate among them throughout the process. Okay, so to summarize today's lecture, actually today we are going to, what we talk about mainly is the process trying to develop. So how do we take in machine learning model of interest and bring them onto the MLC flow? So it's kind of a development part. We start different ways to get models from machine learning frameworks onto IRModule. Our past lectures talk about abstractions. There are different abstractions. We talk about TensorIR, that represents primitive tensor function, library calls, as well as a computational graph that represents high-level computations. We also talk about, in this case, we take a glimpse at high-level primitive operators, so that just like a placeholder to indicate here's operation we want to perform. A lot of the future lectures, again, going to come back to transformations on how we can transform IRModule to make it more optimized. Hopefully, this complete the picture in a sense that we have already talked about the developed, transform, and build and run flow already, and you kind of know what the entire MLC flow looks like. Moving next, we're going to just enhancing the flow to making sure that our transformations becoming more and more powerful. There are other topics that are also interesting as well, as for example, how we can interface with front-end frameworks in different ways. We're also going to touch upon that possibly in the future lecture, and perhaps in some of the supplementary material as well. Okay, so here's the summary of today's lecture. You are more than welcome to check out the lecture notes as well as IPython notebooks. We'll also release certain exercises in a few days to help you get familiarized with the content. And hopefully you enjoy today's lecture. I will see you next week.